This slidecast will cover hash tables. The standard library has a special type of binary search tree called a balanced binary search tree to implement set and map classes. It has order log n access time, and sets and maps can also be implemented using a data structure known as a hash table. It has some advantages over balanced search trees. The goal of the hash table is to access an entry based on its key value, not its location. And we want to be able to access an entry directly through its key value rather than having to determine its location first by searching for the key value in an array. And a hash table enables us to retrieve an entry in constant time. So on average, order 1. That may seem impossible. Let's see how we can do this. Now, the basis for hashing is to take a key and transform it into an integer value, known as its hash code, which is then transformed into a table index. We'll take a key, and the key can be, of any type, and we're going to have an index calculation to turn that key into an integer value so we can do a table index lookup, much like we do for arrays and vectors. Now consider the Huffman code problem in the last chapter. If a text contains only ASCII values, which are the first 128 Unicode values, then we could use a table of size 128 and let its Unicode value be its location in the table. So for instance, an ASCII character would map to an integer value for 128 integer values that we could use as an index for a table of size 128. However, Unicode has 65,536 possible characters, and what if our data allowed all of those values? Well, if we assume that 100 characters are used, then you could use a table of 200 characters and compute the index as follows. You could let the index be the Unicode character mod 200. Now, if text contains this snippet, so suppose we have these terms, and if we have the following hexadecimal or decimal value, say for the right parenthesis, and then the small letter n with the tilde, the indices for those two letters are both 41, because 41 mod 200 is 41, and this 241 mod 200 is also 41. So this would result in a collision. Both of these characters would map to the same index in our table. And we'll talk shortly about how we will handle collisions. Now, in most applications, a key will consist of strings of letters or digits. You can imagine social security numbers or an email address or a partial ID, rather than a single character. And the number of possible key values is much larger than the table size. For instance, if we had all the social security numbers of the students in our class, even though there are many thousands of, tens of thousands, hundreds of thousands of social security numbers, there's less than 100 students in our class. So we don't want to create a table that could hold every possible social security number, because that would be very sparsely populated, might not even fit in the available memory. We want to have a table size that's much closer to the size of the population that we want to store in the tables. Now, the number of possible key values is much larger than the table size in this classroom example. So generating a good hash code is typically an experimental process. The goal would be a random distribution of values, and simple algorithms usually generate lots of collisions. Now, for strings, we could simply sum the character values of all the characters, returns the same hash code for sign and sing, for instance. Here's an algorithm that has had good results using the following formula, where S sub I is the ith character of a string, and n is the length of the string. So cat has a hash code computed as follows. Take each character, multiply it by an exponential involving the prime number 31, and prime numbers generate relatively few collisions. So because there's too many possible strings, the integer value returned by the function can't be unique, but the probability of two strings having the same hash code is relatively small, because the function distributes the hash code fairly evenly throughout the range of integer values. Now, because the hash codes are distributed evenly throughout the range of int values, the function appears to produce a random value that can be used as the table index. And if the object is not already in the table, the probability that the table slot with this index is empty is proportional to how full the table is. Now, although the hash function result appears to be random and gives a random distribution of keys, this calculation is deterministic. You always get the same hash code for a particular key. And a good hash function should be relatively simple and efficient to compute, because it doesn't make sense to use an order n hash function to avoid doing an order n search. We have two ways to organize a hash table: open addressing and chaining. Now, in open addressing, linear probing can be used to access an item in a hash table. And these items are of type pointers to entry types. So if the index calculated for an item's key is occupied by an item with that key, then we found it. And if that element contains an item with a different key, then we increment the index by 1, and we keep incrementing until we either find the key or we find a null entry, if we assume that the table is not full. So here's the algorithm to find an item in a hash table using linear programming. We compute the index by taking the key's hash function mod the size of the table. And if the table subindex is null, then the item's not in the table. If the first item in the pair that's pointed to by the pointer in the table, if it's equal to the key, then we found the item. Otherwise, we continue searching in the table by just incrementing one by one and looking at the next available indexes until we either find an entry with the given key or we come to a null entry. And that indicates that key does not exist in our table. Now, as we increment the table index, we wrap around, just like as if it's a circular array. And this lets us search the part of the table before the hash code value in addition to the part of the table after the hash code value. Now, this could lead to an infinite loop. So how do we know when to stop if the table's full and we haven't found the correct value? So we stop when the index value for the next probe is the same as the hash code for the value. And we ensure that the table is never full by increasing its size after an insertion when the load factor exceeds a specified threshold. So we'll usually have some threshold where once we reach it, we'll expand the table size so that we'll never have a condition where every index entry is occupied. So let's look at a simple example to understand how hash codes work. Here we have 5 names. So names are unique. These are going to be our keys, and we can compute the hash function using the formulas, those sort of exponential formulas with a prime number that we saw earlier. Here's some unique. Here's some numbers for these given strings, and if our table size is only 5, then we take these values and mod them by 5 to get the following hash function values. That means we'll take Tom and place Tom at location 4. When we take Dick, we'll notice location 4 is already occupied. So we'll increment the index, and in this case we'll wrap around, and since slot 0 is available, Dick will be placed there. Next we get Harry, which has a hash function of 3. When we get Sam, Sam also maps to location 4, so we'll start incrementing and checking. Slot 0 is full, so Sam is placed in the first available slot at index 1. Finally, Pete also maps to 3. This is kind of a worst case scenario where we continue incrementing and we have to go wrap all the way around to 2 before we find an available slot for Pete. So here's how we could start with an empty table and 5 items, and we would create our table handling collisions when they occur. Now the retrieval of Tom or Harry takes one step, because for instance when we look for Tom, we generate a hash function of 4 and we immediately find Tom. Now because of collisions, the other retrievals require a linear search. And in the case of Pete, we have to look through the entire table before we can find Pete at location 2. Now here's an insertion example. We've got the following strings, and now we have a hash table of size 10. So Tom and Dick get added at locations 3 and 5. Harry's placed at 10. When Sam maps to 5, we have to increment and place Sam at 6 due to a collision, and then Pete is placed in 7. So there's only one collision that occurred with a larger table. So the best way to reduce the possibility of a collision and avoid the linear search is to increase the table size. Now we can't traverse a hash table in a meaningful way since the sequence of stored values is arbitrary. When an item's deleted, you can't simply set its table entry to null. If we search for an item that may have collided with the deleted item, we might conclude incorrectly that it's not in the table. So instead, we have to store a dummy value or mark the location as available but previously occupied. So deleted items' reduced search efficiency was partially mitigated if they're marked as available because they could be reused. But you can't replace a deleted item with a new item until you verify that the new item is not in the table. To reduce collisions, use a prime number for the size of the table. And a fuller table results in more collisions, so when a hash table becomes sufficiently full, a larger table should be allocated and the entries reinserted. And you have to reinsert and rehash the values into the new table. Do not copy values, as some search chains which were wrapped may break. And deleted items are not reinserted, which saves space and reduces the length of some search chains. So the algorithm for rehashing is to allocate a new hash table with twice the capacity. You reinsert each old table entry that's not been deleted, and then you reference the new table instead of the original. And we'd want to delete and kind of do proper memory management with the old table. Okay, reducing collisions using quadratic probing. Now, linear probing tends to form clusters of keys in the hash table, causing longer search chains. So quadratic probing can reduce the effect of clustering. In this case, we're not going to increment one by one. Our increments will form a quadratic series according to this formula. So our probe number will increment, and then our index will be our start index plus our probe number times our probe number, mod the table length. So if an item has a hash code of 5, then the successive values of the index we'll check are 6, 9, 14. Okay, so we'll use sort of a quadratic series of indexes rather than probing linearly. Now, the disadvantage of quadratic probing is that the next index calculation is time-consuming. We've got a multiplication, an addition, and a mod. So a more efficient way to calculate the next index is this formula. We can add 2 to k, take index plus k, mod the table size. Now some examples: if the initial value of k is -1, then successive values of k will be 1, 3, 5. If the initial value is 5, then the successive values will be 6, 9, 14, etc. So the proof of equality of these two calculation methods is based on this mathematical series, that n squared equals 1 plus 3 plus 5 up to 2 to the n, 2n minus 1. A more serious problem is that not all the table elements are examined when you're looking for an insertion index. So this may mean that an item can't be inserted even when the table is not full, and the program could get stuck in an infinite loop. So if the table size is a prime number and it's never more than half full, then this won't happen. However, that means half of our empty table, having a half empty table requires wasting a lot of memory. So chaining is an alternative to open addressing. So this is another way to organize our hash table, and each table element references a linked list that has all of the items that hash to the same table index. And this linked list is often called a bucket, and we call this bucket hashing. So in this example, Harry and Pete hash to the same table index 3, so they're stored together in a list. And these three entries also hash to the same table entry. Now, the advantage of chaining relative to open addressing is that only the items that have the same value for their hash codes are examined when looking for an object. We don't get these clusters that we had in open addressing. You can store more elements in the table than the number of table slots. And once you determine an item is not present, you can insert it at the beginning or the end of a list. So to remove an item, you simply delete it. You don't need to replace it with a dummy item or mark it as deleted. Load factor is the number of filled cells divided by the table size, and the load factor has the greatest effect on hash table performance. The lower the load factor, the better performance. There's a smaller chance of collisions. If there's no collisions, then the performance for a search is order 1 regardless of the table size, because there's always going to be a list of length 1 for every key. So Donald Knuth derived a formula for the expected number of comparisons, C, for finding an item that's in a hash table that uses open addressing with linear probing and a load factor L. So the expected number is 1 divided by 1 minus L, remember L being the load factor. So the cost would be 1 plus that ratio times 1/2. So using chaining, if an item is in the table, on average we must examine the table element corresponding to the item's hash code. That's the 1, and then half of the items in each list. So that's, this constant 1 corresponds to looking at the, examining the table element, and then half the length of the list on average, where L is the average number of items in a list. Okay, it's the number of items divided by the table size. So here's the performance of open addressing versus chaining. So L is our load factor. The number of probes with linear probing kind of follows this. We sort of start at 1. We've always got to do 1 probe to see if the hash value for a key occurs in an element of our table. All the way up to when we have a when their table's nearly full, we can have on average 10.5 probes. Now with chaining, look at the much smaller growth rate. We start at 1 and then only go up to 1.48. So the chaining gives us a much better performance. Now the number of comparisons required for a binary search of a sorted array is order log n, and a sorted array of size 128 requires up to 7 probes. Okay, 2 to the 7th is 128, which is more than for a hash table of any size that's 90% full. And a binary search tree performs similarly. So our hash table is order 1 expected, worst case order n. The unsorted array is order n, and the binary search tree is order log n with a worst case order n. Now the performance of hashing is preferable to that of the binary search of an array or a binary search tree, particularly if the load factor is less than 0.75. However, the lower the load factor, the more empty storage cells. So there are no empty cells in a sorted array. Now a binary search tree requires 3 references per node, a pointer to an item, and the left and right subtree. So more storage is required for a binary search tree than for a hash table with a load factor of 0.75. Now for open addressing, the number of references to items, meaning key values pairs, is order n, the size of the table. For chaining, the average number of nodes in a list is L, the load factor, and n is the number of table elements. Now using the C++ list class, there will be 2 references in each node, the next and previous, because the C++ lists are double linked list. Now if we use our own single linked list, then we can cut down the references to 1 by eliminating those back pointers. So therefore the storage for n plus L references is needed. So here's an example. Suppose we have 60,000 items in a hash table, a load factor of 0.75. Then this requires a table of size 80,000, and the expected number of comparisons would be 2.5. Now, calculating the table size n to get similar performance using chaining, we would have to have n equal to 20,000. So a hash table of size 20,000 provides the storage space for 20,000 references to lists, and there are 60,000 nodes in the table, one for each item. So using a single linked list, this requires storage for 60,000 pointers, and this is the same storage as needed for open addressing. And that brings us to the end of this slidecast.